Okay, we're in section 16 of the notes, and this is going to be about adding together the terms in a sequence. And we're going to be doing both a finite sum and an infinite sum. There is some overlap here of what you've done in Math 120. In Math 120, you were introduced to sequences in series. And what you did with the sequences is that you added them together. All right, that's for a finite. You'll also bridge the gap from finite to infinite in Math 120 by talking about the geometric series. All right, we'll go through that. So, certainly I'll talk through the notes. I'll go to the whiteboard and do that. But I will say this, it's really easy to be misled. And that could happen to anyone, all right? I recently watched a video, a physicist who was talking about a sum, and they were intentionally trying to mislead people, by the way. And it was kind of like humorous to watch, but I think a lot of people would watch that and they wouldn't see the humor in it. They would see more that these people were showing something that was utterly ridiculous, and they might even buy into it, all right? But anyway, here's the deal. We're going to talk through the notes at the whiteboard. I'll go through some historical notes. No, we're not actually memorized too much, but the bottom line is we'll talk through the notes and we'll talk about historically the perspective here. We have better ways of doing what was done historically, but the bottom line, it's nice to have a little history behind this. We're going to talk about, a series for an infinite series. We're going to talk about the nth partial sum of a series. We're going to talk about the geometric series, again, at the whiteboard. We'll talk about what's called a telescoping series, and we'll do examples of that as well. All right. Once we get through this, though, our goal is to, introduce the concept of what a converged series is. All right. And we'll have a really simple test of divergence, which generally speaking is not very helpful. But anyway, it's something that's really easy to show and something you're going to be using anyway. Then we'll get to examples. First lecture, though. Let me go to lecture. And I'm going to share the whiteboard with you. And we'll talk through it. All right. So my claim over here is this. Again, this reminds me of the, that talk the physicist gave, and this is a YouTube video where they were showing something I thought pretty outrageous, but they used a similar argument. Right now, they were kind of being jokesters about it, but I'll write down not the series they gave, but I'll write down a series over here. So I want to tell you what the sequence is. The sequence is pretty easy. The sequence is 10. 100, this is a sequence, by the way, 1,000, whoops, sorry about that, 1,000, yada, 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 that's the sequence. The series, of course, is going to be when added those together. It's going to be infinite. This is 10 plus 100 plus 1,000 plus yada, yada, yada. Well, any sane person looking at that would say, oh, this thing is going to blow up. It's going to go off to infinity, all right? Now, what the physicists did was this. Again, they've used a different series, but that's incidental as far as I'm concerned. What they did was they did this. They look at something like this over here, and they said, well, it's an equation. So if we treat both sides the same way, that's fine. So what do? They multiply both sides by 10, which might seem odd to you, but it's easy to do. What would you get? Well, 10 times 10 is 100. 10 times 100 is 1,000. And then you get 10,000. Yada, yada, yada. Then what they did, they said, okay, let's subtract the two. And what would you get? You would get 10s minus s. Like after all these equations, it's legitimate. And you study for, finite equations, one that have a finite number of terms in it, that this is a reasonable thing to do, right? You've been told that. You've been taught that since you're beginning algebra. Now, what would you, if you did this over here, the left side's pretty easy to do, 10s minus s. And then what are you going to get? Well, if I did that, well, what would I get? Well, I'm looking at it. I'm going to say the terms would all disappear, except for that initial term, which is 10. All right. All right, so 10s minus s is 10s minus s. Oops, I made a mistake because I was subtracting, right? So it's minus 10. All right. So again, I'm subtracting. What do you get over here? 9s equals minus 10, or s is equal to minus 10/9. This is crazy. It really is. And there's a problem with this. We can't do this. And the thing is, this is going to be the bridge you get from, finite all the way up to infinite. right, number of terms. And there's something really profoundly wrong about what we just did over here. We may not know what it is at this point, but this is profoundly wrong. All right. Let me give you another example. And the other example I want to give you is if we had this series to write down, and I'm going to write down for you. I'm going to put the sequence down for you. The first term is 9/10. The next term is going to be 9/100. The next term in the sequence is going to be 9/1000. And this goes on forever. That's a sequence. If I were going to write the sum down for this, that's a series, I would get 9/10 plus 9/100 plus 9/1000. I think you get the idea. And this goes on forever. Well, if I did that, what would I get adding them together? It's pretty easy to add together, by the way. You get 0.999. That goes on forever. All right. Now let's do our S again with the multiplication. I'll put this over here. S is 9/10, 9/100. You did this in Math 120. And what they did was they multiplied both sides by 10. What would you get? 10s. What would you get there? You get, if you multiply by 10, right? You get 9 plus 9/10 plus 9/100. What do they do now? They subtract them. And what do they get? Well, let's write it down. 10s minus s. What would you get over there if you subtract it? Again, what I'm pointing out is, I'm subtracting. This disappears, so forth and so on. So what you left off with? Just a 9. That's not so bad. And now what do you get? You get 9s is equal to 9, or s is equal to 1. By the way, for a lot of people, this also looks like madness, but this is true. This is equal to 1, identically. It's identically equal to 1. All right. Now, from grade school, other ones like this. I'll put another example down. From grade school, this is equal to 1/3. From grade school, this one too. That's equal to 2/3. So forth and so on. There's some some you don't know. Now, when you took Math 120, they did this by using a geometric series or by using, I'm going to say, a middle school technique that some teachers teach, other teachers don't. I certainly teach that middle school technique because it's so nice. Let me go through that middle school technique. And if I were to write this down and say, I don't know what the number is, I would multiply both sides by 10. Then I'd subtract. And then I'd say X is 1. That's my middle school technique. Now, granted, in Math 120, they actually went through the geometric series to do that, which we'll talk when we get there. But that's one technique they use in Math 120. All right, we go back to the notes. And what I'm going to talk about now is another really deceptive type series. The sequence of numbers, I'll write them down for you, is 1, 1/2, 1/3, 1/4. You get the idea, yada, yada, yada. It goes on forever. But then someone says, I wonder what the sum is. The sum is going to be 1 plus 1/2 plus 1/3 plus 1/4 plus yada, yada, yada. Well, I'll be honest with you, there's no amount of manipulation I'm going to get that to cancel off. All right. So at least not that I can see. So then the question comes is, well, we'll play around with it. So what we do, and by the way, it's called the Harmonic Series. And this is a very important series, a series that we're going to use often. So it's nice to know, what it converges to or what it does not converge to. In other words, it's not convergent, doesn't go to any particular sum. But it's certainly nice to remember this one. All right. And again, I'm not actually to memorize. Sure, have like I recall something that we've done like this before. But anyway, what I did over here, which might seem crazy to you, this one over here, I actually had a machine add together, 1 plus 1/2 plus 1/3 plus yada, yada, yada. And I stopped at 1/1,000,000. All right, how many terms you got there? 1,000,000. Yeah, 1,000,000 terms. Computers can do this, by the way. And they said it was about this number over here, 14.4. All right. Then what I did 10 to the 12th. Right. So I'm going to tell you what that like 1 plus 1/2 plus 1/3 plus yada, 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 plus 1/10 to the 12th. All right. And certainly I did it on a computer, and then it turned out to be 28.2. So forth and so on. And the computer didn't do this pretty quickly. That's 10 to the 24th. It's a large number of terms. Like the number of terms over here is 10 to the 12th. The number of terms over here would be 10 to the 24. And I'm seeing this pattern over here. Now, what do I notice about this over here is just looking at these things, the more add on, it seems like the bigger and bigger it gets, but it's not getting big quick. It's not getting big quick. All right. Now, a machine did this, a machine. I did not do that. Now, whether I'm using Sage, Mathematica, I don't think a calculator can do it. A laptop computer, a cell phone could do it, yada, yada, yada. They'd be pretty much, I'm going to say it's pretty easy to add things together in a computer because computers are really good at adding. So what I want to talk about is this guy that probably had a lot of free time in his hand and also was probably pretty bright. Now, I don't know much about him, but this guy was from France, a Catholic bishop. My suspicion is the guy had some free time on his hand. All right. Now, what do I mean by that? He was able to play around and, write things up, publish them. And, maybe he had some duties to do, but he probably had a pretty cushy life, being taken care of, having not to worry about a job. I mean, a real job, a job where you have to, work. I'm not saying what he didn't do was work, but like when I say real work, physical labor, something difficult. This guy had I'm going to say a cushy job. All right. So what he does, he thinks about it. And he starts to look at it and he says he needs a convincing way to show people that this is going to blow up, that it doesn't go to any finite sum. And we're kind of looking at this thing using a machine, and I'm looking at this thing and I'm saying, yeah, for me, it's clear as day that the more terms I add on, the bigger and bigger and bigger and bigger it's going to get. It's going to blow up. And my suspicion is going off to infinity. So what I want to do is go to the next page, and he put the series down. And then he started to look at it, and he did something like this over here. And I'll talk about that on the next page. Again, we're hoping you can understand what we're talking about over here. So, I'm just going to underline what he's looking at. So he's definitely looking at the series, right? The harmonic series. And the harmonic series, I'll write down for you, is the sum n equals 1 to infinity 1 over n. And what he's trying to show that this thing blows up without bound. He's trying to show that. He's trying to show that this thing gets bigger and bigger and bigger. Well, he doesn't have all the time in the world. He can't go to infinity. So he has to start reasoning about that. So what does he start to do? He starts to write the terms down. So he writes the first term down. This is the first term of it. That's the second term. And then he groups, right? He groups, and let me put this down. This is A1. This is A2. This is A3, A4. I think you get the idea. Then he gets A5, A6, A7, A8. All right, he gets this over here. Then he starts to think about what he wants to do is he wants to find something a little bit smaller than that he can actually add together. All right, so a little bit smaller. Now, certainly 1 is equal to 1. This is a perfect mapping. That's not smaller. A half is equal to a half. But then he looks at the 1/3 and the quarter and he says to himself, well, why don't I just make everything quarters? So what do you have? You have 1/4, that's smaller than a third, right? And 1/4, it's exactly the same size. So now he has a sum that's actually smaller. All right, so I'm going to call this the sum n equals 1 to infinity 1 over n. And this one here, this here, is actually larger. I'm sorry. I mean, I got that backwards. I got the arrow in the wrong direction. I got to erase that. It's crazy to say that. I'm going to say this. Whoops, sorry about that. This one is larger. All right. So let's take a look at this guy. What is he doing now? Well, the first 2 terms he puts down, then the third and the fourth term down, he groups them together. And he says 1/4, and 1/4 is certainly smaller than 1/3 plus 1/4. Then he looks at the next ones, and he's going to group these. This is going to be a grouping of 2. This will be a grouping of 4. So the last term there is an eighth, so he makes everything an eighth. All right, so this is equal. If I look at this one, and again, what I'm seeing is 1/8 is smaller than 1/7. 1/8 is smaller than 1/6, and 1/8 is smaller than 1/5. Now, what would the next one be? Right, if I did it, if I put the next term down, I put a plus sign over here, cross this out. So let's put down, you get 1/9 plus 1/10. Let's just talk about it. 1/11 plus boom, boom, boom. Where would he stop? Let's take a look at it. 4/8/16. All right, I'll put on doing it. 4/8/16. How many terms would be there? Let's count them up. 9, 10, 11, 12, 13, 14, 15, 16. There'd be 8 terms. So what would he do? He'd say 1/16. We see 8 of them. I don't want to write down 8 of them. I'll just do 8 times that. And what does he start to notice now? He starts to notice that each one of these groupings that he's done, let me write this down for you. 1 plus 1/2. But every grouping that he does there on out adds together to 1/2. 1/4 plus 1/4 is 1/2. 1/8, 1/8, 1/8, 1/8 is 4/8, which is 1/2. What's 8 times 1/16? 1/2. He can get an infinite number of groupings of a half. Infinite number. Infinite number. Keep going on and on and on. So here is where the convincing argument comes. That these guys over here, if you keep looking at it, what are you getting? 1 plus 1 plus 1. And again, he's just grouping these two together. It's a bunch of ones. How many ones? An infinite number of ones. What's an infinite number of ones? It's equal to 1. So what did this guy show? He showed that this series here is divergent. It does not add up to a finite number. All right, that's important. You want to remember that. All right, let's talk about the next thing up, which is, you're going to be given a series, and we'll talk about what the series looks like. And not that we always start with 1, but typically it's nice to start at 1. So we have a given series. That's what they look like over here. We're summing terms together, A1 plus A2 plus A3, and it goes off to infinity. What do we like to do like times? We'd like to look at the nth partial sum. And what's that going to be? We stop at some finite number n. So it's going to be A1, A2, A3, but we're stopping at AN, right? Just like we did with the harmonic. We stopped at a finite number of n when we introduced the concept. All right, I'm going to do a geometric now. And this is something you did in Math 120. So you did this in Math 120. All right, let's write it down. So it's going to be the geometric sequence. I'll put this over here. Well, typically we start somewhere, and we typically start with some number A, and then we say, oh, to get the next one, you just simply multiply on some number R. To get the next term, you multiply on some number R again. So the next term would be R squared. And you would do this, yada, 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 until you got to the nth term. What's the nth term going to be? The formula would be A. Well, let me point this out. This is A1. This is A2. This is A3. That's what you did in Math 120. What's this one going to be? R to the n minus 1. All right, now what are they going to do? They add it together, and it's fairly easy to do to add this together. I'll write it down for you. This is the sum of the geometric. We're going to call this a series now. Let's write it down. What do you get? A plus AR plus AR squared. And this is going to be the nth partial sum. Okay. What do you get over here? I'm sorry, dot, 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 up to A. And again, this is the nth partial sum. All right. What are we adding together? We're adding the terms together, A1 plus A2 plus A3 up to AN, which is the nth partial sum. Okay, so let's write this down in kind of notation we'd like to write it down. This is the sum. Let's see, little n equals 1, not to infinity, but to some finite number n. So what do you get over here? A sub n. So if you did this, you're going to get, A1 plus A2 plus A3. It's the nth partial sum. Now, the question is, you may remember this. You may not remember this. You may have no recollection of what you've done in Math 120. It happens. What I got to do is I got to figure it out. And let's go through it one step at a time. So I'm going to write this over here. And I'm going to say, Sn is equal to A plus AR plus AR squared plus yada, 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 plus A to the Rn minus 1. What I'm going to do is multiply both sides by that R, which in Math 120, this was called a common ratio. And if you did that, what would you get? You would get this nth partial sum times R equals AR, right? I'll put that over here, plus AR squared plus AR cubed plus yada, 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 up to, well, if you multiply the last term by R, what would you get? You would get AR to the nth power. Let me write Sn down again for you. And what's Sn again? Well, I'll write it down for you. It's A plus AR plus AR squared plus yada, 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 up to ARn minus 1. All right. I know this is difficult, by the way, but we're going to do the same thing. We're going to subtract. All right. So what I'm going to do, I'm going to write this down for you. We're going to write down, I don't know, there's many ways you can subtract. I'm just going to write Sn minus R times Sn. And let's take a look. I see the subtractions now, right? And I'm going to say I'm left with an A, and this term's going to disappear, and there'll be a term over here disappears, and this one will make this disappear over here. So what do you get then? Well, you're left with something, aren't you? You're left with minus A R n minus 1. Let me repeat this. I'm subtracting. So this one, take away this. This one, take away this. There's something here, take away this. There's something here, take away the one right before it. What are you left off with? A minus A times R to the, I'm sorry, I made a mistake in the copy. Get my eraser out. Right there, it's got to be erased. My mistake. All right, let me point this out to you again. We're left with this guy, and we're subtracting this guy. All right, so someone said, what are you going to do now? Well, I want to get Sn. So I'm going to factor it out. And you're going to get 1 minus R. I'm going to factor the A out. Not that you have to, but it's nice if you can. 1 minus R to the n. And I can divide both sides by 1 minus R now. What do you get? A 1 minus R to the n over 1 minus R. This is exactly what they did in Math 120. And that was for the geometric. Let's go back to the notes. Make sure you understand what we just did over here. So what do we just do? Oh, geez, I didn't do what I said I was going to do. Infinite. Let's go for it. So how do you do an infinite now? And I got to look at this and wonder, what is, oh, I'm sorry, this is Sn. To be infinite, what I got to do is I got to look at the limit as this big N goes off to infinity of Sn. I'm going to call it for the time being S infinity. There's a trouble over here. Now that's what the trouble is going to be. Limit. I'm sorry. I think I made a mistake in the notation too. Yeah, you know what? I want to go back to lowercase n because I noticed my formula has the lowercase n in it. And I got to just erase this over here. Sorry about that. My eraser out again. And I got to erase this business over here. Yeah, I do that sometimes. I start to mix letters. And I got to erase this guy now. Oops. Let's see, Sn. All right, another one to erase. Oh, boy. All right, let's write this down. Limit as, oh, I got another n to erase. I got a little confusing. I want to be consistent though. Let's see what we got over here. A, 1 minus r to the little n, 1 minus r. Well, n is now going off to infinity. So I'm looking at this thing and I'm going to say there's only one term that's related to the n, all right, that the n's working on. And I want to outline that for you. It's this term over here. And for this limit to exist, I want that term to disappear. So I'm just going to pretend it disappears for the time being, and then write down what the result would be if it disappeared. It would be a over 1 minus r. But the only way this would disappear is if r were called a proper fraction. Now someone says, what does it mean by proper fraction? That it's the absolute value of it would be less than 1. Well, now we're back in the territory of math 119. The r, for this to be true, must be between -1 and 1 to meet that condition over there. If that's the case, we'd get this sum over here, all right? So we just kind of did a little bit of review of what you did in math 120, all right? You did finite sums and you did infinite sums, and we just derived that for you. So this is done. Let's go to the next page. And next page says, try to find if the series is convergent. Now, this is not geometric, and I got to be honest with you, this could be really, really difficult to do. Sums in general are nearly impossible to come up with. And you might say to yourself, well, if it's impossible, why do you even try? We have a lot of examples where they do converge to these finite numbers, and we're looking for that. So let's take a look, and let me write down S1 for you. And I'm not opposed to using a computer, by the way, but I want to see if I can write that down. It's going to be 1 over 1 times 1 plus 1, which is 1/2. That's done. Let me write down S2. S2 is going to be 1 over 1 times 1 plus 1 plus, when I go to the next term is going to be 1 over 2 times 2 plus 1. And yes, I know this is tedious. This is 1/2 plus 1/6. What's that going to be? Well, it's going to be 6. 3 plus 1 is 4, 6, which is 2/3. All right. All right, let's put down S3. Well, S3, I get this. 1 over 1 plus, 1 times 1 plus 1 plus 1 over, we just did that, didn't we? And then I wrote the next term on, which is going to be 1 over 3 times 3 plus 1. Well, you know what? What's nice about this? I already did the first two terms. It's just simply 2/3. And what am I adding on now? I'm adding on 1 over 12. All right, let's see if we can do that. And again, the reason we do this, we're writing things down. We're seeing if there's patterns to it. Maybe there's no pattern. Maybe just completely confusing. But 12, that would be 8 plus 1, which is 9/12. That would be 3/4. All right, let's check and see if we did it right. 3/4. All right, let's do S4. Well, it's just going to be the prior guy, which was 3/4, plus the very next term now. Get a little better at this, which would be 4 times 5. Well, what do you get over there? 3/4 plus 1/20. And this gets more difficult. Each one I add on gets more and more difficult. Well, I'm going to say 20 is a common denominator. That's going to be 16 over 20. Yeah, you need to know grade school arithmetic. That'd be 4/5. Well, miracle. Right. I'm not going to bore you with the rest of the detail. However, you're more than welcome to do it for you. Just come by during our session and do it. But the next one will be 5/6 and then 6/7. So looking at this over here, I'm going to make a prediction that S big N would be equal to, well, looking at it, and again, what I want to point out, I'm not saying it's true. I'm just saying I'm seeing something. Like this is 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So I'm going to make an impression that this is probably going to be N. And what's the bottom going to be? Let's look at it. 1 more than, whoops, I didn't mean to do that. one more than the top, 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 one more than the top. So I'm going to say, hey, probably n plus 1. Oh, I keep doing that. Probably. All right, then the question comes is, what would S infinity be if this is true? Well, I take a look at a limit. As my big N goes to infinity, n plus 1, what would that give me? 1. All right. So what I want to do is I want to talk about what they're suggesting I do. They're suggesting I use partial fractions to do the problem. And I want to write that down for you. And this is going to be the sum. I got to make sure I'm doing the right thing. Little n equals 1. Off to infinity. And this would be 1 over n plus 1. Well, here's what they do. They do what's called a finite sum, a partial sum. So I'm going to write Sn down. And that's going to be equal to n equals 1 to big N, 1 over n plus 1. Now, they do mention that partial fractions might be helpful. So I want to put this over here. And if someone says, I don't even remember doing partial fractions, we did that when we did integrations. Now, they were very useful for integrations. They're going to be incredibly useful for sums. So what I write over here, A over n plus B over n plus 1. Multiply both sides by the LCD, you would get 1. Then you'd get A times n plus 1 plus B times n. Then I would choose an easy n. I would say n is 0. What would you get over here? You would get 1 equals A. So I know A is 1. Let me get my eraser out, and I'll put that down for you. Let's see if we can figure out what B then is, all right? And more difficult. So I'm going to say n would be, I don't know, n would, whoops, sorry about that. N would be minus 1. What are you over there? 1 equals minus B. Well, now I know B is minus 1, and I'll put that down for you. Let me eraser out. Okay, so let me write this over here then. This would be the same thing as the sum, n equals 1 to big N, 1 over n minus 1 over n plus 1. Again, we used a partial fraction decomposition to do that. I'll put this in parentheses. And then what they do is they start writing terms down. Now I'm going to do this, basically starting with 1, then going to 2, then going to 3. What if I start 1, what I get 1 over 1 minus 1 over 2. Well, I could do that, but that's not the point. What's next one going to be? 1 over 2 minus 1 over 3. Let's keep going. What's the next one going to be? 1 over 3 minus 1 over 4. I think you get the idea. 1 over 4 minus 1 over 5. But at some point you say, okay, I get the idea, but when is it going to stop? And let's take a look at it. It's going to stop at big N. So it's going to be 1 over big N minus 1 over big N plus 1. You got it? Okay. What's the guy that comes before this one now? Will be 1 over big N minus 1 minus 1 over big N. And by the way, there's a lot of stuff going on in the middle here, but I'm not really too concerned about it. What I'm concerned about is there a nice simple pattern? And there is. If you look at it, I get an awful lot of cancellations in the problem. And I'm hoping you realize without me writing them all down, which would be impossible to do, I get a lot of cancellations in the problem. All right. And what would I be left off with if I did that? All those cancellations, in the end, you'd be left off with 1 over 1 minus 1 over n plus 1. All right. What do you get over here? Common denominator, n plus 1 minus 1 which is n over n plus 1. Did we believe that? We sure did. We believed that looking at the finite sums that we were doing before. So then the big question comes is, how would you get S infinity? Well, what I did over here, and we've already done it. So we're getting 1 over here. Not so bad. It really isn't that bad. Let's go to the very next page, see what we have. We'll talk about this. We'll talk about it in stages. And again, we're going to encourage you to read the notes, read over the notes anyway, but convergent property of series. So what they say is if you have two series and they converge and K is some constant. So what are we saying? What does converge mean? That they actually add up to some finite number. They actually add up to some finite number. And K is some constant. That's all they said. Where they say, well, willy-nilly, you can add them together. That's nice to know. Willy-nilly, you can just simply multiply by constants. That's nice to know, right? Move things around, add them together, multiply by constants, yada, yada, yada. All right. So furthermore, changing a finite number of terms in a series does not change whether or not it converges, although it may change the value of its sum if it doesn't converge. This is real dangerous. Do not commute terms around. Don't do any groupings in a series unless you absolutely know it converges. All right. So let's go to the next thing up, test for divergence. Although not terribly useful in the long run, it is the simplest test possible. And let's read through it. If the sum of the nth, if the limit of the nth term is not equal to 0, or if the limit is dne, we can conclude that the series is divergent with little to no effort. Let's look at the proof. Okay. Suppose we have a convergent series with some s. All right. What does it say? Over here, let's read it through one step at a time. The limit as n goes to infinity an would be this. Let me explain this to you. So someone says, what's the difference between Sn and Sn minus 1? Well, let me write this down for you, and I'll be careful. Sn would be A1 plus A2 up to AN. What's Sn minus 1? Well, it's going to be A1 plus A2 plus yada, yada, yada up to AN minus 1. All right. So what are they doing over here? They're doing Sn minus Sn minus 1. Well, if I saw that, basically they're subtracting. And what happens? You get a tremendous number of cancellations. Would that be agreed? All right, here comes the problem. What comes before this term? It's an minus 1. That would cancel that. What are you left off with? An. So I'm agreeing with this statement over here. All right, I'm agreeing with it. All right. So what do? They split it to two different limits. And what are these limits going to be? Well, they're infinite limits. It's just going to be S infinity, or I call it S. It's got to be 0. So what do we know? If we have a convergent series, that limit must be 0. However, it does not imply that if the limit is 0, that the series converges. This is where a lot of students get screwed up. This does not, whoops, I didn't mean to do that. This does not imply that the series converges. A good example of that, harmonic. We know it diverges, but the limit as of the nth term as n goes to infinity is 0, but it's still a divergent series. All right. So that's often problematic for students. But the bottom line is, over time, I gotta be honest with you, this test is not terribly useful, but I'll be honest with you, it's a simple one, and I'd like to do it. What am I hoping for? That the limit as n goes to infinity, the nth term, is not 0, or that it doesn't exist. And I just simply say the series is divergent, and I'm done with it. There's nothing left to do. All right. All right. That's about it. We'll go to examples next. Thank you for paying attention.